In 1907, Einstein had another new idea, stimulated by Planck's law for blackbody radiation. He thought he could derive a new formula for specific heat or heat capacity in solids, which is temperature dependent. Einstein's new formula was experimentally confirmed in a wide range of temperature, but his prediction for low temperature was noticeably underestimated. Why? 5 years later, Einstein's formula was refined by Debye, who, in passing, soon succeeded Einstein as an associate professor of theoretical physics at the University of Zurich. Welcome to Yun Tuition. I am Yun. Let's have a closer look at this historical issue to see how it was theoretically fixed. Are you ready? Let's go and have fun. Unlike gases, atoms in condensed matter are localized. They vibrate or oscillate locally around their balance positions. As temperature increases from 0 Kelvin, the total vibration energy of atoms increases. The slope is defined as the heat capacity, namely capacity equal to the first derivative of the internal energy, U. Specific heat is also called the heat capacity if you know the amount of material. Obviously, the formula for heat capacity can be derived once formula for the total internal energy is known. In principle, one could simply heat up the vibration energy of every atom in solids to obtain the internal energy. But one must know the energy for each oscillator statistically in the first place. Based on the equal partition theorem in classical physics, Dulong and Petit derived the heat capacity for solids as CV equal to 3R, where R is a universal gas constant. So is the heat capacity. However, Einstein knew the equal partition theorem is invalid, as shown in deriving the Planck's law for radiation. So he contemplated with the formula for mean energy in the Planck's law instead. Finally, he created his new formula for the heat capacity in his first draft, or perhaps on his scratch paper. Where I use X denote h nu over kT, h a Planck constant, nu the frequency of atomic oscillations, k Boltzmann constant, and T temperature of the sample in Kelvin. Anyone who can do the first derivative could easily derive Einstein's new formula if they knew the same idea. That's why idea is important. Indeed, the rest of the talk is about how Einstein's original idea in his first draft was artistically refined by Debye, although new concepts were created by Debye to justify his doing. Notice the frequency nu in Einstein's new formula is a single value parameter called Einstein frequency, unlike that in Planck's law for blackbody radiation, which is continuous from 0 to infinity. Einstein assumed all atoms in lattice of the solids oscillate at this frequency. Such ideal solids are called Einstein's solids. Please remember this. For Debye, who had also intensively investigated Planck's law, must have considered this Einstein's assumption oversimplified, unrealistic. So it's Debye's turn. Debye argued that atoms that form lattice may oscillate at a slightly different frequency range called dispersion from 0 to certain cutoff frequency, now called Debye frequency. More importantly, he thought atoms in different positions of lattice may oscillate with different phases as the sun travels in media. Sound is often treated as waves, but the Debye thought sound wave in sonnet could be mathematically treated as virtual particles called phonons. In this way, he might think Einstein's idea could be justified somehow, namely using the mean energy formula in the Planck's law for photons to describe the vibration excitations in terms of phonons. As a matter of fact, after Bose proposed his quantum statistics in 1924, it would appear that both photons and phonons can be treated as bosons, the term first coined by Dirac to acknowledge Bose's contribution to modern physics. Now, return to Debye's work. His cutoff frequency allows him to generalize Einstein's original formula for the heat capacity. How? As shown in this diagram, vertical axis is for density of states, or DOS for short. It gives a distribution of quantum state at different energy or frequency values. For example, all quantum state in Einstein's theory for heat capacity is located at a single energy value, whilst the density of state in Debye's theory spread between 0 and his cutoff frequency. So what is the connection between Debye's general theory and Einstein's special theory on heat capacity? To help you to see the connection, here I prepare this general equation, which can be used to derive both Einstein's formula and Debye's formula in terms of density of states, G. In particular, the density of states for Einstein's formula can be written as a Dirac's delta function, G sub E equal to delta nu minus nu sub E, whilst the density of state for Debye's formula can be written as a quadratic equation, G sub D proportional to nu square. Why does Debye's formula provide the better prediction for heat capacity at a low temperature region? Well, because Debye's density of states is much more realistic compared with that used by Einstein, relatively speaking. Nevertheless, many experimentally observed DOS in different samples differ from that introduced by Debye as shown in this diagram. This implies there is no general formula for heat capacity of condensed matter. Disappointed? Unnecessary. By its very nature, natural science is a never-ending process of discovery. So, humans' exploration will continue forever, irrespective of emerging AI. In fact, neither Einstein nor Debye explain their assumed equivalency of thermal and radiative processes. Can anyone tell their fundamental difference? Is Einstein's ideal sonnet, namely all atoms oscillate at the same frequency, equivalent to Planck's virtual blackbody? I leave this question for younger researchers. I still remember an author wrote from Book 4, New Concept English, the textbook I used to study English in China. The talent goes into the first draft and the art into the drafts that follow, concerning how a writer writes a book. Similarly, one ought to distinguish the talent and the art when watching talks or films on science. My brief talk here is focused on the talent, namely the idea of physics in creating the quantum formula for heat capacity by the two great physicists. Of course, the related art, namely tons of mathematical equations, can be found in many books and papers of the past century if you have time to read. Thank you for watching. See you next time.